Alright, hi Year 12s, this is Mr. Lim here again, and this is our third video on changes to one chemical species. Let's start. Okay, I'm not wasting time on this, you can copy that down this later. Alright, so graphing changes. So we've discussed that we are changing one concentration of one substance within the equilibrium system, alright? And therefore, we should recognize that one of the rates of the reaction will initially spike, which means that it just changes rapidly, up or down, all right? Because you're either going to add something or remove something from the system, depending whether it's a reactant or product is which reaction is going to be affected, all right? However, if one of them changes, that means the other rate of reaction, the reverse or the forward, the other one remains unchanged. And we have to kind of remember that if you don't change the concentration of those reactants for that reaction, that reaction rate is not going to change. It's going to stay constant, even though the other one changes. Then over time, they will become closer together until they are at equilibrium. Okay, so remember, there's a reason why a reaction rate which is going faster will eventually slow down, because the concentration of those products or the concentration of those reactants will lower, and so therefore the reaction rate will slow down, right? And the other one will speed up because there's more of those reactants being produced, and therefore they'll match rates at some point in time, right? And that point in time is when dynamic equilibrium is established. Okay, so let's have a look at an example. All right, here's a rate of reaction graph. You can see that there's a forward and reverse rate of reaction, which are going equally at the beginning, which means that it's at equilibrium. Okay, then all of a sudden you see that the forward rate of reaction jumps up. Okay, so the forward rate of reaction jumps, also known as spikes. I'm going to call it spikes from now on. Okay, so the forward rate of reaction spikes. Why might the forward rate of reaction spike? So let's think of it. We have reactants and we have products. The reason why the forward rate of reaction would spike is because you've added more reactants here. Okay, so you've added more reactants, there are more collisions, and so therefore there are more successful collisions. Remember, when we say collisions, what word do we also need to say? Frequent, so that increase the frequency of collisions for reactants, and therefore you have a faster rate of reaction. Okay, so the forward rate of reaction jumps or spikes, and the reverse rate of reaction stays constant. Okay, so you see there, it stays constant at that instantaneous point in time. All right, so at this point in time here, that point in time, T1, we would say that the forward reaction is favored, right? We would also say that the forward reaction is increased. And the reverse rate of reaction is unchanged, meaning that there is a net forward rate of reaction. All right, then the forward rate of reaction slows down, the reverse rate of reaction speeds up, until we reach dynamic equilibrium again, somewhere between here and here. So here again, we have equilibrium. All right, so between there and there, we have equilibrium. And then what happens at this point in time over here? What happens? The reverse rate of reaction spikes down. The reverse rate of reaction spikes down. What could cause the reverse rate of reaction to spike down? Let's back up here. Right, what could cause the reverse rate of reaction to spike back down would be if you remove some product, which would lower the concentration of products, which are the reactants of the reverse reaction, and that would slow down the reverse reaction. All right, so that reverse rate of reaction spikes down. At this point in time here, T2, which reaction is favored? The forward reaction is favored because the forward reaction is going faster than the reverse rate of reaction. Did the forward rate of reaction increase? No, it did not. The forward rate of reaction did not increase, however, it is still favored. So the reverse rate of reaction went down, forward rate of reaction remained the same. There is a net forward rate of reaction, which means the forward rate of reaction is favored, even though it did not change. All right, then again, the forward rate of reaction goes down, the reverse rate of reaction goes up, and therefore we hit equilibrium again here, and it's equilibrium all the way until that endpoint. All right, so that's just about graphing. These spikes, okay, so a couple of things. I've drawn this terribly because I haven't been bothered getting a ruler out, but if in a test, you will have to draw this with a ruler. All right, so ruler here, ruler here, ruler here, ruler here, ruler here. Everywhere there's equilibrium, or if there's a spike, you should draw it with a ruler. Okay, in terms of drawing your curves, all right, what you're aiming for is a kind of a duck bill shape, all right, or I don't know how to describe that shape. It's that shape there. Okay, so make sure you get those gradients as close to perfect as you can. And it shouldn't stop changing until you hit equilibrium. Okay, so if this one here started like this and then like that, compared to the red one, and the red one didn't change, this, you would say that this one stopped here, and therefore that would be an incorrect diagram if you drew that horizontal line from there. Okay, so they've got to kind of flatten out at the same point in time. Okay, let's move on. Okay, so that was rate of reaction graphs. Now this is concentration graphs. So in concentration graphs, one of the substances will spike up or down. That makes sense because we've just either added or removed some, right? And the other substances, because there might be more than one, will remain unchanged. Okay, because you didn't do anything to them when you change one substance. Then after that point in time, they will increase or decrease depending on the net rate of reaction. Okay, so everything else changes depending on the net rate of reaction. Let's have a look at an example here over here. All right, so I have my three substances, A, B, and C. All right, so I can see that they were at equilibrium. They were at equilibrium between the starting time and that point there. Why? Because their concentrations weren't changing. Okay, that's how we can tell that they were at equilibrium. Then at that point in time over here, let's call this T1. What happened to the system? I removed some C. So here, this indicates that remove some C. Okay, when you remove the C, you've decreased its concentration, and therefore the reaction where C is a reactant will slow down, and the reaction, and therefore the other reaction will be favored. All right, so let's have a look here. So if we're trying to work out which ones are on the same side, we've got to look at how the lines have moved. Okay, so you can see here that C went up, A also went up, and B went down. Okay, that implies that if C goes up after it was being removed and A goes up after being removed, it means that the A and C are likely to be on the same side of the equation. All right, A and C are likely to be on the same side of the equation because they're both being produced by the favored net reaction. All right, and therefore B is probably on the other side. All right, so let's have a think. If I removed some C, in this particular rate of reaction, then the forward rate of reaction would decrease, the reverse rate of reaction would stay the same, and there would be a net, reverse rate of reaction. Okay, a net reverse rate of reaction in that reaction there would produce more A and C and consume some B, and that's what this graph is showing. Okay, so let's move on. At this point about here or so-ish, right, equilibrium was established again, and there you go, flat lines again, because they're at equilibrium. However, at this point in time here, T2, okay, we would say that what has occurred, I've added some B. Okay, if you've added some B and this is the equation, what's going to happen? Right, I added some more B, which is a product. That means I have increased the rate of forward reaction. Okay, what happens? Sorry, what I add some B? No, that's not the forward rate of reaction, the reverse rate of reaction. I've increased the reverse rate of reaction. If I've increased the reverse rate of reaction, what happens to the forward rate of reaction? Did I change anything about A and C? No, I did not. So the forward rate of reaction stays unchanged. Okay. If the reverse rate of reaction is increased and the forward rate of reaction has stayed the same, there is a net, forward or reverse? Reverse rate of reaction. Okay, there's a net reverse rate of reaction. And if there's a net reverse rate of reaction, there's going to be more A and C produced. Okay, more A and C produced, and B is consumed. Okay, so let's see that. B was consumed, so you can see that curve down there. But now I need to draw A and C being produced, which will look like that, and A, which will look like this. Okay, so I've drawn that purposely wrong. Who can see why? Yeah, actually, it's not that bad, actually. All right, I was trying to go for this not hitting equilibrium at the same time as each other. All right, and you can see that, yeah, kind of, it doesn't really hit equilibrium at the same time. Also, we should try and draw this with a little bit more curve as well. Okay, so that's definitely not there because you can see that that equilibrium there is a bit too early. Okay, so I should try and redraw that with that arcing up until there. Okay, so that's the idea. You can show this with concentration graphs as well, where the concentration changes and we have to think about the rates of reaction which have changed and therefore work out the net rate of reaction and work out what's changing. Let's move on. Okay, changes to concentration graph. Dynamic equilibrium is established when concentrations cease to change. Okay, so that's again equilibrium when it flatlines. Okay, initial change will not be fully returned to original value, but close to that original value. Okay, so what does that mean? Look over here. So this one here at C went down by that much and went up by that much, which is slightly less than the original amount. Okay, so it's never going to return past the original amount. So if this one changed by this much, this one only changed by a little bit, not by a lot, right? But it definitely couldn't change by that much or something like that. Okay, so you can't change more than you changed initially. And the changes in concentration, have to be in stoichiometric amounts. Okay, so what does that mean? It means that if you look here, all of these changed by about this much, which is hopefully quite similar. Okay, they all changed by about that much. And if they all change by about the same amount, that means they all have the same coefficient, 1, 1, 1, or 2, 2, 2, whatever. But like, no, it's definitely 1, 1, 1, right? So they're all going to change by the same amount. But let's have a look at this graph over here, which I've drawn before. Okay, so here I have A plus B makes 2C. Okay, what have I done at the very beginning? I have added A to the system, right, which will increase the forward rate of reaction. And the reverse rate of reaction does what? Absolutely nothing. There is a net forward rate of reaction. And if there's a net forward rate of reaction, that means that there is more products produced and reactants consumed. Okay, so what will happen after this point in time? Well, if the forward rate of reaction is there's a net forward rate of reaction, there's more product produced, the reactants are consumed, so that A, being a reactant, will be consumed. So we'll slow down like this. Okay. And then B will do the same thing. We'll go down by the same amount. But C will go up by twice as much. Okay. So if this is how much it goes up by, I need to go up by twice as that, which would be, yeah, maybe that, something like that. Okay, so that there is 2x if that is x. And it's perfectly fine to mark out that how many times that's going to be in your test, just to show that you understand that kind of. All right, I haven't done a very good job of where this equilibrium has started. Right, but you should try and do better, especially if it tells you that equilibrium is established at time, whatever, over down there. All right, so that is what it means by the concentration changes have to be in stoichiometric ratios. Okay, and then finally, you should be then, if you ever get a graph and trying to work out what change it is, it should be fairly easy. If you see one spike, okay, one spike, then it's going to be a one chemical species change, okay? And that's fairly obvious now, but later on when we get to temperature and concentration, you're going to have different amounts of spikes and stuff like that. So therefore, you have to think about which one is it. And this one here is just going to be a one spike because you see one spike here, right? And if it's a one spike over here, what has occurred? I've removed one, right? Which one have I removed? So let's have a think. This one went up, this one went up, this one went down. So it's likely that one of the two that went up of what is the side that has two substances, which means that these are the reactants, reactant 1, reactant 2, right? We'll see that the B line went down by a lot, okay? And these ones went up by only a little, okay? Because they are the reactants, they have a coefficient. Now, since these two go up by roughly the same, this coefficient here, this coefficient here is likely to be the same as that coefficient there, which happens to be 1. So if that's 1 there, that's going to be 1 there as well. All right. So that's how we do that. Sorry that's such a long video, but this is a difficult concept. We'll go through this in class and we'll see how we go. Adios.